Hello friends, today we will discuss transistor characteristics and configurations. Before discussing the transistor characteristics, first we will start with semiconductors. Semiconductors, first version in the semiconductors used is the vacuum tubes. Vacuum tubes is the heavy biggest one, it will take a large space. Inside the vacuum tubes we have filaments. So, electronic equipment is worked with the vacuum tubes in the beginning, but as it is taking more power and taking more space and our life span time is very less, means it is not using for many days. So, we are avoiding these vacuum tubes and we are started with the transistors. Vacuum tubes is the cost more, whereas transistor cost is less. So, compared to the vacuum tubes, the best next version we used is the transistor. Transistor is one of the semiconductor device. It is uses 3 terminals: emitter, base, collector. So, before emitter, base, collector discussing, actually what is transistor? Transistor is used for the amplification of the electrical signals. What is the means of amplification of electrical signals? Actual input signal is there. The input signal strength is weak. So, after sending from the transistor, the signal strength is improved. The signal strength is improved, that is called as transistor. This transistor is invented by the scientist John Borden in 1947. So, before transistor, which one we used? Before transistor we used vacuum tubes. These transistors are used for controlling the electrical signals. A transistor, full form of, what is the full form of transistor? Transfer resistor, means resistance value is transferring from input side to the output side. In these transistors we are using the term called junction transistor. In this junction transistor, 2 types of transistors is there: unipolar transistor, bipolar transistor. What is the meaning of unipolar transistor? Only one type of charge carriers is there. Only either majority charge carriers is p type or minor or n type. 2 types of charge carriers we have, p type and n type. In p type we have holes, in n type we have electrons. So, current is passing through only one type of charge carriers, that is unipolar transistor. Next we have bipolar transistor. In bipolar transistor, both type of charge carriers are participating, both majority charge carriers as well as minority charge carriers is using in bipolar transistor. So, transistor means only use bipolar transistor, not unipolar transistor. Again this transistor is formed using p-n junction diode. 2 p-n junction diodes we are using this one. In this transistor, bipolar junction transistor is used. So, this bipolar junction transistor is abbreviated as BJT, and this is the current control device, and we are getting output as either voltage we are getting or current we are getting, and useful for the power controlling devices. And here the current, whatever we are using across the current, across the input is called as input current. Here we have 2 types of transistors. The first one is PNP transistor, next one is NPN transistor. In PNP transistor, this PNP transistor and NPN transistor both comes under junction transistor. In PNP transistor, the across the 2 sides we have P material, in the middle we have N material. Here it is, transistor is of 3 terminal device. What are the 3 terminals we have? Emitter, base, collector. If I am keeping the base in the middle, that is called as a common base. If I keep emitter in the middle, I will call it as a common emitter. If I keep collector in the middle, we will call it as a common collector. So, 3 ways we are differentiating the transistor. It is either common base, common emitter, common collector. Whichever is using in the middle term, we will call that as a configuration. So, this in this 3 terminal device, PNP transistor, N is in the middle, 2 edges we have P. So, here how many depletion regions is forming and how many PN junction diodes we have? PN is one combination. So, one PN junction diode. NP is another combination, another PN junction diode. So, in this PNP transistor, we have 2 PN junction diodes. So, if 2 PN junction diodes, 2 depletion regions is forming. Where these 2 depletion regions is forming in this image? One depletion region is forming across PN, another depletion region is forming across NP. So, if depletion region is there, some potential barrier will be produced, that is about PNP transistor. So, you can write emitter terminal, collector terminal, base term with exchange, that is our option. Whatever is in the middle, we will call it as that configuration. Again we have another type of transistor. In another type of transistor is NPN transistor. Here which combination is forming? One combination is NP, another combination is PN. Across NP is one PN junction diode. Again PN combination is also another PN junction diode. Here also two depletion regions is forming and potential barrier is there. Again it is conducting or not conducting, that is based on forward bias or reverse bias. So, if you take the transistor, how to differentiate whether it is PNP or NPN and which type of transistor we are using in our laboratory while doing practicals. Now, we will see. First type is PNP transistor. One terminal is P, which is across the top section connected to the collector, and N is connected to the base, another P is connected to the collector. Now, here the major important part is arrow. If arrow is inside, that is PNP transistor. Whereas for check for the NPN transistor arrow is out. So, here I will raise one doubt, how we are deciding this arrow inside or outside. Arrow is always opposite to the electrons. For PNP transistor, N is in the middle, is it? N means electrons. If electrons is there, the corresponding arrow we have to keep opposite. So, arrow is upward for PNP transistor, for arrow is outside, arrow is for NPN transistor. So, we discussed about two transistors, PNP transistor, NPN transistor. Now, we will see the working, what is the difference in working of PNP transistor and NPN transistor. So, before that just the terminology, what are the terminology we are using? One term is emitter, another term is collector, the next term is base. If we are keeping emitter, whatever the corresponding current, I am calling it as a emitter current, and it is represented with I times of E. I means current, E means emitter. So, the emitter current is represented with IE and the collector current is represented as IC. What is C here? C is collector, I is current. Next, another current we have, that is called as B, IB current. IB means base current. Out of these three, base is very lightly doped. Whereas suppose I want to measure the current IC, in practical I will use for the collector current IC milliammeter, as well as for collector current IC I will use milliammeter, MA. While taking readings I have to put the option in milliammeter, whereas suppose I want to measure the base current IB current, at that time I had to keep my switch in microammeter, not in milliammeter. Why we are keeping this base in milliammeter means this base is very lightly doped, it is very sensitive element base. So, if heavily doped it will break down. So, we had to make this one as very lightly doped one. So, out of emitter base collector junction, middle one is base. If I am using emitter base as a one part, that is called as emitter base junction. Another, in the middle what we have? Base, the corner side we have collector. So, if I am taking base collector combination, that one is called as collector base junction. So, from input to the output side, two regions are forming. If I am taking the combination of emitter base, it is called as emitter base junction. If I use the combination base and collector, it is called as collector base junction. So, two types of junctions is forming. Whatever the current across the emitter, that is emitter current. Whatever the current across the base, that is base current. Whatever the current across the collector is collector current. Out of these three, base is very lightly doped one. Next, we will see the different transistors which we will use in the laboratory. So, how many terminals we have transistors? 3 terminals, emitter, base, collector. So, how to identify which transistor is which one? So, in the practicals while doing, you just cross check the number which one we have to use. Suppose example, for transistor characteristics I am using BC107 transistor, which is the last one in this image. Just check 3 terminals we have with a small notch across the one end. What is that notch represents? That notch is emitter. So, we have 3 terminals. While doing practicals, the 3 terminals are looking same. So, how to treat which is emitter, which is base, which is collector? To the transistor, wherever you have notch symbol, notch means small curve is there across the end. Wherever you have the curve across the end, that terminal we have to use as emitter, the middle one is base and the last one is collector. However, we had to keep the resistors while doing practicals for input side as well as output side. So, these are the different versions of the transistors. After seeing the different versions of transistors, now we will see how it will works, how PNP transistor is working, how NPN transistor is working. In PNP transistor, PN combination is forward biased, NP combination is reverse biased. Forward biased means P means positive. So, I have to apply the power supply as positive negative across the positive. Just see the image. In the image we have 2 power supplies. One power supply we are using is VEB, another power supply we are using is VCB. VEB power supply is forward biased, VCB power supply is reverse biased. If VEB supply is forward biased, positive with P, what it happens? Forward biased. Forward biased PP is ripple. So, it is moving towards the N terminal. If it is moving towards the N terminal means it is coming across the base terminal. So, from P to N it is moving, again from N to P it is moving. Just check the second power supply. We have P terminal and power supply is negative. P with negative means it is reverse biased. So, the first junction is forward biased, second junction is reverse biased. P with first power supply is repelled, P with second power supply is attracted. So, it is moving towards the second power supply. When it is moving towards the second power supply, what happens? Covalent bonds are breaking across the first junction. When covalent bonds are breaking across the first junction means here the covalent bonds are breaking across the PN junction. When covalent bonds breaking across the PN junction, electron is trying to move towards the positive terminal. If electron is trying to move towards the positive terminal, some hole will be there, because electron is moving means nothing is there. That nothing means some space is created. The space is called as a hole. So, this is the working of PNP transistor. In PNP transistor, holes are moving towards the N. Some recombination of electron hole pairs is taking place due to minority charge carriers. Remain holes are moving towards the P section. This P is combining with negative terminal of the battery, and which actually it is attracting due to the reverse bias. What happens? Electrons are created, and those electrons are covalent bonds, are actual covalent bonds are generated. Those covalent bond electrons are moving towards the positive terminal of the battery. Some hole is created, that hole is moving towards the N type of the battery. So, this is the working of PNP transistor. Next we will see the working of NPN transistor. What is the difference between PNP transistor and NPN transistor? In NPN transistor, first N means electrons, P means holes, again N means electrons. The first junction is forward or reverse. The first junction is forward biased, second junction is reverse biased. To keep forward bias, N terminal means which power supply I have to use? Forward means minus minus. So, I am using power supply is minus to plus. Based on NPN or PNP transistor, we have to keep minus plus terminal or plus minus terminal. So, what happening? These electrons are moving towards the P side, electron hole recombination takes place. Some of the small amount of recombination will be takes place because base is lightly doped. Remaining electrons is moving towards the N terminal, and that is combining with the VCB power supply. We have positive voltage. So, those electrons are combining with the VCB positive voltage here. Whenever recombination is takes place, one electron is generated across minus terminal of VEB. Here VE power supply, which terminals we have? Minus and plus. So, whenever recombination is taking place, from minus terminal electron is generated, that electron is moving towards N plus. This is the working of NPN transistor. We will recall once again, in NPN transistor, N consists of electrons, P consists of holes, again N consists of electrons. N and P recombination is taking place, but small amount of addition is there. Remaining electrons is moving towards the N. This N is combining with power supply voltage of VCB, electron hole recombination is taking place. Whenever recombination is taking place, an electron is produced across VEB, that electron is forwarding or passing towards the N plus junction. This is the working of NPN transistor. Next we will see the different transistor connections. As we know, NPN is there, PNP is there. In this NPN, PNP, whatever in the middle I am keeping, that configuration we will use. If in the middle I am keeping B, that is IB. If in the middle I am keeping emitter, that is IE. In the middle if I am keeping collector, that is IC. So, your option whether you can use in the practical, whether we can use NPN transistor or PNP transistor, but concentrate on which configuration we are using. Which configuration you are using is based on your middle connection, that is transistor connections. Next, after transistor connections, we will go for individual one. What is the first transistor connection? We have common base transistor configuration. Here, which is input terminal, which is output terminal, which is middle terminal. Emitter is input, base is in the middle, collector is across the output. Whatever the current we have across the emitter, that is input current IE. Whatever the current we have across the collector IC, the current across the B is IB. So, which voltmeters I have to keep in this diagram? Suppose I am using voltmeter across emitter to base. So, what is that voltmeter? VEB. Voltmeter is placed from E to B, then we will call that voltmeter as VEB. If I keep voltmeter from C to B, that is called as VCB. So, here we have again this is two subcategories, one input characteristics, output characteristics. Input characteristics, which current meter we are using in this diagram? The current meter I am using is IE. The voltmeter I am using is VEB. So, variation of from the diagram, variation of IE with VEB. In the output voltage I am keeping constant. So, here which is constant? Voltage from collector to emitter is constant. So, input characteristics by this graph and previous diagram correlate, then easy to learn. Here across the input we have emitter and base. So, I am using voltmeter as VEB, current meter as IE. Across the output I am keeping constant VCB, that comes under input characteristics. So, x axis which I am taking, across x axis I am taking VBE, y axis I am taking IE. For which is fixed constant here? Here voltage from collector to base is constant. Here different voltage of collector to base you perform, one you keep 0 volts, another you keep 8 volts and another you keep 18 volts. Here input resistance is very small, output resistance is very high. Input resistance, initially just observe the readings, initially VBE I took 0, 0.2, 0.4. So, initially no current is flowing. As we are increasing voltage, VBE voltage, the current start flowing, small variation is there, small variation of current is taking place. So, which is x axis, which is y axis is the important parameters here. What is the input current? Input voltage. Which one you are keeping constant? So, input current IE versus VEB at constant VCB, and input resistance is very small. This is about common base input configuration. Next we will see common base output characteristics. From the previous image, now here what we can say from the previous image, previously we concentrated on only input side. Now, we will concentrate on output side. In output side, what are the parameters we have? Output side, the current parameter is IC, the voltage parameter is VCB. So, how we have to take IC versus VCB? In output parameters what we have? IC we have, VCB we have. So, IC versus VCB, which one we have to keep constant here? Keep IE as a constant. So, IC versus VBC with current IE is constant is called as output characteristics. See this image, x axis what we have, y axis what we have, what is constant. In the output what we have? Voltage is VCB, current what we have? IC current. Which one we have to keep constant? IE is constant. So, again this diagram is divided into 3 categories. What are the 3 categories it is divided? First one is active region, second one is saturation region, third one is cutoff region. What is active region, what is saturation region, what is cutoff region? In active region, from the image we can say that in active region, from V, which one is increasing? VCB is increasing and IC is increasing. We are getting flat curves. Just observe the image, all for different values of IE, the lines are very flat. So, the region between positive axis side, we will treat it as a active region. And next one is saturation region. In the saturation region, for the small variation of VCB, current is increasing rapidly. Just observe in this VCB from 0 to minus 1, 0 to minus 1, current is increased sharply, whereas across the positive axis current is constant. So, saturation region means negative x axis, we will treat it as a saturation region, positive x axis we will treat it as a active region. Next, one more region we have. What is one more region? Cutoff region. What is cutoff region? Suppose I am keeping input current IE equal to 0. If input current IE equal to 0 means actually collector current also has to be 0. Input side I kept current 0. Actually what we have to get? Collector, output collector current is also 0, but we are not getting collector current 0. Small variation of value is there. That small gap we will call it as a cutoff region. So, total 3 regions: active region, saturation region, cutoff region. Active region means positive x axis is treated as active region, negative x axis is treated as saturation region. Small gap is there between x axis and for IE equal 0 milliamperes, that is called as cutoff region. Actually it has to touch to the x axis, but it is not touching to the x axis, that is the cutoff region. This is about output characteristics. So, we discussed common base configuration, input characteristics as well as output characteristics. Next we will see the next configuration. What is the next configuration? We have emitter transistor characteristics. In common emitter transistor, which one is in the middle? Emitter is in the middle. So, I am calling this as a common emitter. Again the description of common emitter, common base, common collector is almost same. So, the description can be elaborated by seeing the diagram. Here which terminals is using across the input? IB is using across the input. So, that is base current is your input. Which current we are using across the output? Collector current we are using across the output. So, the collector current is IC. Again we will see the input characteristics, output characteristics. From the diagram, IE versus VBE. What is IB? Input current. What is the voltage we are taking? VBE. So, IB versus VBE, which is constant? Output voltage is constant. Here the output voltage is VCE, that is about your input characteristics. Just by seeing this one you will understand what we are taking x axis. X axis I are taking as voltage from emitter to base. VEB is x axis. What is input current? IB. Just in this, why IB is in microamperes, why not in milliamperes? This is the important point here, as IB is lightly doped. So, very small amount of current is flowing. Suppose in the practical, if you keep IB in milliamperes, the current will be not displayed, only for the microamperes only it is displaying. So, here the variation is non-linear variation is observed across the input terminal. Same way we will see the output terminal. So, I will raise one doubt here. What is the difference between the output characteristics of CB configuration and CE configuration? In CE configuration, what is the graph? Saturation region gone to the negative side of the x axis. This is CB. Whereas in CE, what is the diagram? In CE, it is not taking along the x axis. It is taking only in the positive side of the region. So, that is the main key point you have to mention in the examination. In CB region, the saturation region is towards the negative side, whereas in CE region, the saturation is not going to the negative x axis. The sharp increasing of current is taking place only for the 0 voltage. Just observe this point here. For 0 volts, the sharp increasing of current is taking place, and one more thing is here the current is constant. 10 milli, I only suppose for 1 voltage I am taking. Suppose cutoff region you take 0. Across 0, what happening? For 10 microamperes current, it is increasing from 0 to 1. It is not going further, again it is continuously flat curves is appeared, means constant we are getting. So, here the variation of VCE versus IC across constant base current IB we are taking. This is about the common emitter configuration. Next we will go for the common collector configuration. The common collector configuration is almost same as common base and common collector, just concentrate on which is input and which is output. Here which is input? B is input, means IB is input. Which is output here? Emitter is output. Which is connected to ground? Collector is connected to ground. Again same way, here we are taking x axis variation and output variation. The difference between the common emitter, common base and common collector is here the collector current is decreasing. Just observe the previous diagrams. In the previous diagram the current variation is non-linear, increasing. X axis, y axis is increasing, non-linear. Even in the common base also x axis, y axis is increasing, which is in non-linear. But for the common collector the current is continuous, sudden drop decreases, that is shown in this figure. Straight lines it is looking, means current is decreasing for the input characteristics. Again in the output characters we have saturation region, active region, cutoff region. So active region means input is forward bias, output is, here we have to remember three. Active region means input is forward bias, output is reverse bias. Saturation region means input and output both are in forward bias. Again cutoff region means input, output both are in reverse bias region. So these are the configurations we discussed: common base, common emitter, common collector. Next we will see current parameters. We are using two current parameters, alpha and beta. This alpha is used for common base configuration. What is the definition of alpha? Alpha is the current amplification factor, alpha equal to IC by IE. IC means collector current by emitter current at constant VCB. Same way we have beta also. Alpha is using for CB, beta is using for CE. What is the definition of beta? IC by IB, IC by IE, which is keeping constant, VCE is keeping constant. Main important point here is alpha value is less than 1, it is from 0.95 to 99, whereas the beta value is greater than 1. These are the two current parameters we have to concentrate. Using this we have some current formulas. First, input current IE equal to IB plus IC, and alpha value, beta value. Using IE equal to IB plus IC, defining alpha in terms of beta. What is the formula of alpha in terms of beta? Means we have to write alpha equal to beta by 1 plus beta. What is the formula of beta in terms of alpha? Means beta equal to alpha by 1 minus alpha. So these are the 5 formulas related to the current as well as current amplification factors alpha and beta. Next we have hybrid parameters. What is the purpose of using these hybrid parameters? Hybrid parameter is represented with H, first thing, and again we are using for low frequency applications. Suppose I want to calculate input impedance, output impedance. Instead of calculating input impedance and output impedance, directly you can use your hybrid parameters. The hybrid parameter values is almost equivalent to your input impedance values as well as output impedance values. Using these hybrid parameters values, we can manufacture the transistors. Next, this is the configuration of hybrid parameters. In the hybrid parameters, I am using 4 parameters called H11, H12, H21, H22. One is input admittance. What is H11? H11 is input admittance. These 4 formulas is written from the expression. We have one voltage equation and one current equation. What is voltage equation? We have V1 equal to H11 I1, H12 V2. I2 equal to H21 I1, H22 V2. Just if you want to write H11, neglect H12. Just see the first equation what we have. V1 equal to H11 I1, H12 V2. I want to write H11. From that I am taking V1 by I1. Suppose I want to write H12. To write H12, I am taking V1 by V2. Suppose I want to write H21. To write H21, I am taking I2 by I1. To write H22, I am taking I2 by V2. So H11 is input impedance, H12 is forward current ratio, H21 is reverse voltage ratio, H22 is output impedance. Input impedance is represented with HI, forward current ratio is represented with HF, reverse voltage is represented with HR, output admittance is represented with H naught. Using this, we can write these H parameters again in CB configuration, CE configuration and CC configuration. Again we have to convert from these H parameters from CE to CB, CC to CE, means out of 3 1 by 1 configuration, convert from CE to CC, again convert from CC to CB, again convert from CB to CE. So, these are the final values we will get after conversion. This is about the conversion of H parameters. After conversion of H parameters, we have different values for each parameter. What is its input impedance? What is its forward ratio, reverse ratio, output impedance, what is the input resistance, total values is mentioned in this. So, where we are using these transistors, without transistor there is no electronic equipment. Final conclusion is without transistor no electronic equipment. Single battery inside the chip to the large scale electrical equipment, everywhere nowadays we are using transistor. There are many variations of transistor, based on the application we are using the different types of transistor. So, final conclusion, what is transistor? Transfer resistor is the transistor. In this transistor we have PNP and NPN and we have 3 configurations. Before discussing 3 configuration, 3 emitter, base, collector, common base, common emitter, common collector. In each side we are checking input as well as output. Again we discussed about hybrid parameters. Thank you.